Our design objective is to produce an air pressure powered bottle rocket that maximizes flight time while keeping a payload undamaged. We solve this using simulation software to gather effective data and SolidWorks to combine our ideas into a model.
The rocket uses elastic potential energy stored in the air to generate thrust. By ejecting the water and air through the nozzle, it applies an equal but opposite force on the rocket described by Newton's third law. Impulse is the product of force and time, also known as the rate of change in momentum with units Newton-second. Impulse describes how quickly a change in momentum is experienced. The greater the impulse, the more energy is transferred to the object as either the magnitude or duration of the force is increased. Water extends the thrust duration, thus increasing the impulse. Air on its own, in contrast, provides a more powerful, shorter burst of thrust that diminishes quickly. As you can see, increasing water fraction increases the impulse up to a limit where there is no longer enough air pressure to generate significant thrust.
Directional stability is a rocket's ability to maintain a straight and stable trajectory during its flight by tending to move back to its original direction when influenced by outside factors such as a wind. This can be affected by factors such as fin size and shape, nose cone, overall shape, weight distribution, and the parachute system used. Specifically, larger fins provide more drag, which moves the centre of pressure further away from the centre of gravity, making it more stable but slower than smaller fins. This is only the case when the fins are placed at the back, behind the centre of gravity and near the nozzle.
Terminal velocity is the speed at which an object moves through a fluid while the resultant force acting upon it is zero. It's mostly affected by the shape, mass, and cross-sectional area of the object. Varying the parachute area increases the terminal velocity by increasing the amount of air being caught in the parachute's cross-sectional area. Increasing the parachute cross-sectional area does increase the mass, which slightly increases the terminal velocity while the parachute isn't deployed and decreases the launch velocity. Eventually, as the parachute size gets larger, complicated arise because the parachute is so large that it might not deploy properly.
Considering all the data we've collected and applying it to the rocket should optimise for flight time, we have however made sacrifices to the flight time to ensure that the rocket does not fail after launch. This will lead to the rocket being optimal in terms of structural quality as well as flight time. More specifically, the data has led us to these rocket features. It should use a 2-litre Dr Pepper bottle, 0.79 meters as a parachute diameter, 0.59 water fraction, triangular fins, one 4-fin and one 3-fin rocket that we are making, which are approximately 0.006 meters squared per fin. In the real world, there are build errors that the simulations don't account for, such as how build quality can affect the trajectory and structure of the rocket. Other examples could be faults in manufacture causing unwanted movement in the rocket affecting the trajectory, parts not being glued down strongly enough reducing directional stability, subpar application of hot glue reducing integrity of the pressure vessel increasing chance of an explosion, loose connections in the parachute string which increases the likelihood of drastically shorter flight time and damage to the egg, the parachute doesn't open instantly, wind direction doesn't stay constant and can change speed and direction suddenly. The rocket could be damaged between the build and the launch phase, so repairs must be possible and quick. This rocket will be built over 4 to 6 hours to safety specifications and using this model as a guide.
In conclusion, we've learned how using simulation software such as Excel and Unity can help rapidly improve and optimize a design, how constant iteration and testing on every design choice can ensure the quality of a final design, and how real-world factors have to be accounted for during the design phase, as simulations can't always account for issues such as low build quality.